We're going to start talking about chapter 2. And chapter 2 is all about derivatives. So we're going to talk about the derivative and tangent lines. One thing the derivative does is it gives you the slope of the tangent line at a point. And derivatives are actually found by using limits, which is why we start everything with limits. So the limit definition of a derivative is this. And here, that's the notation for a first derivative. You can take more than first derivatives, you can take second derivatives and third derivatives. We'll talk about what those are eventually. But right now we're just talking first derivatives. So this is the notation for a first derivative. And what you say here is you say f prime of x. So this isn't a 1, it's sort of a tick right here. Okay, so it's f prime of x. And then this is the limit definition of a derivative. And it should look familiar because we have done it. We just never called it the definition of a derivative. We just called it this random formula that we're using. The difference now is because it is technically the limit definition of a derivative, now when you're asked to find the derivative using the limit process, you have to have this formula memorized instead of being able to look at it, okay? There are a few different notations for first derivatives. You have this one, which is f prime of x. This is a super popular one. You have y prime. I personally don't use y prime a lot, only because you run the risk of forgetting the tick and it just becomes another y in the problem, and that makes it confusing, so I like to not do that. And then you have dy dx. This is the derivative of y with respect to x. This is popular where it gets used for something called implicit differentiation. We do that later. So that's one that I definitely would know. And then another one is when you have the derivative with respect to x of f of x. This is one that you mostly see for formulas. So the ones that I'm most often going to use would be this one and this one. The other ones exist. It's worth having seen the notation, but we're not really going to use it all that much. Okay? So in terms of examples, we're going to find the first derivative. Using the limit process. So let's say f of x is x cubed 3x squared plus x. Okay, so the first thing you have to do is you have to plug it through the formula. So you've got the limit as delta x approaches 0, and you're plugging it in. So f of x plus delta x, you want to replace your x's with the x plus delta x. So you have x plus delta x cubed minus 3 times x plus delta x squared plus x plus delta x. Minus, in parentheses, so you remember to distribute the negative, f of x needs to go here, which again is this part. All over delta x. So then, like we did before, when we were simplifying the stuff, you need to multiply everything out. So you want to cube this, square this, distribute the negative 3, and distribute your negative sign here. And as many steps as you need to take to not do those things wrong. So if you cube it, you've got x squared plus 3, cubed, plus 3x squared delta x plus 3x delta x squared plus delta x cubed. You'll square this and distribute the negative 3, so then you've got minus 3x squared minus 6x delta x, I should have written smaller, minus 3 delta x squared plus x plus delta x, and then minus this, which I'm going to smush in here, but it's this right there. So So minus x cubed minus plus, just distribute your negative, 3x squared minus x, sorry it's small, over delta x. Okay, so then like you did before, you want to look for terms that will cancel out, and stuff should cancel out to be 0. Remember, if stuff combines to be like 2x cubed, you did something funny. So you've got x cubed and negative x cubed, which is nothing, 3x squared and negative 3x squared. Not that one. Sorry. That would be nothing. Positive x and negative x is nothing. So then you want to look at what you have left, and what you should notice, that one, that one, that one, that one, that one, that one. Every single term of what you have left has at least one delta x in it, so you want to factor that out as your overall greatest common factor. Keeping in mind that you need to make sure that you're writing the limit down, because until delta x goes in, you can't just erase the limit portion. So you've got delta x, here you've got 3x squared, here's plus 3x, and now you're down to 1 delta x, here you've got 2 of them left, you've got minus 6x, you've got 1 left, this is now plus 1, and this right here is the mistake that people tend to make because they just disappear the term. Make sure that you don't disappear your terms. So then delta x can cross out, and you're left with this. So at that point, you want to evaluate your limit. So you're going to put in 0 for all of your delta x's. So if all of the delta x's become 0, that'll do away with this term, and this term. And at that point, you're left with 3x squared minus 6x plus 1, which is your first derivative. Eventually, we'll learn rules, and by eventually, I mean like tomorrow. We'll do rules that'll get you from here to here without all of the stuff, but for right now, we're doing all of the stuff so that we can practice with the limit process. So we're gonna do a couple more of those, just for practice. Then we'll talk about a few other things that have to do with derivatives, and then that'll be it. So this one should be easy, but people always do some weird things with it. So let's say that f of x is 3. Fine. So we've got the limit as delta x approaches 0. We've got f of x plus delta x, which is just 3, minus f of x, which is just 3 over delta x. Fine. So then you've got 0 over delta x. So then you've got 0, because 0 divided by anything is 0. And the limit as delta x approaches 0 of 0, it's just constant, would be 0. So then that would be your derivative. I like to do this one because for some reason people have trouble going from this step to this step. So I like to make sure that I've shown it so that you don't make it weird when we get there. All right, one more. Okay, so you've got your limit. As delta x approaches 0, you want to start out with f of x plus delta x. So instead of x, you have x plus delta x minus the exact function over delta x. So here you have both square roots and fractions. The first thing you want to do is you want to make common denominators before you go about trying to put the conjugate in. So if you're trying to make common denominators, this one needs the square root of x plus 5. This one needs that part. And then you want to look at what you have. So then you've got 2 square root of x plus 5 minus 2 square root of x plus delta x plus 5 over. So it's over that and that. And remember, when you have the compound fraction like that, you can take your two denominators and put them together. I would write this in front so it doesn't go over here and get lost. All right, so now you're at the point that you've dealt with the fraction, you need to deal with the square root. So to get rid of the square roots, you need to put the conjugate in, remembering the parentheses so that it means what you want it to mean. With the plus sign in the middle as its conjugate. Then you multiply at the top, never multiply at the bottom because that will always make things worse. So when you're multiplying at the top, the 2 and the 2 is going to make it 4, and then the square roots will go away. So you'll want to distribute the 4 into this, distribute a negative 4 into the other one, and remember that the square roots are gone at this point because you're basically just doing FOIL. So you got 4x plus 20 minus 4x minus 4 delta x minus 20 over all that nonsense. And now, like you always do, you should be able to get rid of stuff. So 20 and negative 20 is nothing. 4x and negative 4x is nothing. Here, you just have negative 4 delta x. Here, you have delta x, you want to get rid of it. That's still a triangle. It's just looking sad as time goes on. So you've got negative 4 over this nonsense that you're left with. Make sure, because it's a weird but commonish mistake, when you are putting the conjugate in, don't forget to put it on the bottom. Don't just put it on the top. That will mess everything up a lot. So now you put in the zeros for delta x. So then this is 0. That one's 0. So you still have the negative 4 on the top. So you've got here square root of x plus 5 times, since this is 0, square root of x plus 5, which is just x plus 5. Here you've got 2 of them and 2 more of them, which means you have 4 of them. Square root of x plus 5. And then that technically is your first derivative. It would be a good idea to take the one tiny extra effort and get rid of the 4s, okay? So then your final first derivative would be negative 1 over x plus 5 and the square root of x plus 5. And you can write it like this. It's a nice thing to realize that this means that because you have 1 1/2 of them, you could also write it like this and have it be to the 3/2. Either one is fine. It's nice to know that those mean the same thing, but if you leave it like this, no big deal, okay? So that is flat out finding the derivative using the limit process. Now we're going to relate it to tangent lines and slope. So we're going to find the slope of the tangent line at a given point. That's supposed to be at, but I got lazy. You can rewrite it as at. Okay. We're going to do 2 of these. you're looking to find the slope of the tangent line, the slope of the tangent line is the derivative. That was the first thing that I talked about. So that means that you have to find the derivative. Now, right now, the only way that you know how to find the derivative is by using the limit process. So that's what you're going to have to do. It's nice because you get more practice doing all of that algebra. So to find the first derivative, we've got the limit as delta x approaches 0, and you have to do all of that, okay? So same thing, you'll distribute everything, including the negative sign. Please don't forget the negative sign. That's 0, that's 0, trash of delta x. And then same thing, this confuses people. I'm never quite clear why, but it does. So you have no more delta x's, fine. The limit as delta x approaches 0 for 2/3, it's gonna stay 2/3. Fine, so right now your first derivative is 2/3. To find the slope of the tangent line at the point, what you then do is you would plug in your x value to your derivative, and that will give you your slope. Well, if my derivative is just a number, then that means my slope is just that number because I have no x's to plug in, which is fine, okay? So we're going to do one where we actually can plug in x. I like to do this because it throws people off for some reason. I want to make sure that you know what's going on. Okay. So same thing, we're trying to find the slope of the tangent line at the given point. So here's your equation, here's your point. First thing you need to do is you need to find the derivative. Right now, the only way that you know how to find the derivative is by using the limit process. So we're going to do that. So you've got f of x plus delta x minus f of x over delta x. And you want to multiply everything out. So here you've got x squared minus 2x delta x because you're distributing that negative minus delta x squared minus 7 plus x squared because you're distributing that negative. And then you want to get rid of stuff. So x squared negative x squared is nothing. 7 and negative 7 is nothing. These both have a delta x, which you want to factor out. And get rid of. Fine. So then you can plug in 0 for delta x. That will get rid of this term because it'll turn into 0. So then your first derivative is negative 2x. This one does have an x. So to find your slope, you need to plug in 2 because that's your x value to the derivative. So we're going to find f prime of 2 is 2, which is negative 4. So then that is your slope for the tangent. Okay? So we're going to change up the problem a tiny bit. Instead of finding the equation, or instead of finding just the slope of the tangent line, we're going to go through and find the equation of the tangent line. But really it's super simple because if you have the slope and you have the point, you just want to use point slope form and write the equation of a line. Okay? We're only going to do one of those just for practice. But really the hardest part is getting through the algebra of finding the first derivative, but we've done that so often by now, you should be pretty decent at it. There's going to be the difference. So instead of just finding the slope, we're actually going to go through and find the equation. So let's say that f of x is 4 over x. And our point is going to be 4, 5. This is kind of like the limit stuff where the beginning notes are going to be long. I'm sorry. So you want to find your derivative, so you've got to go through your limit stuff. You've got 4 over x plus delta x minus 4 over x over delta x. So same thing, because it is a fraction, you need to make common denominators first so you can squish everything together. So this one needs an x. This one needs the x plus delta x, and we'll put in parentheses where they belong. Squeeze. Okay, so then you're looking at 4x minus 4x minus 4 delta x over this and this, so same thing, you can put them together. So you've got x and delta x and x plus delta x. So 4x minus 4x is nothing. You can clear delta x. So then you're looking at negative 4 over x times x plus delta x. You want to evaluate the limit and plug in 0 for delta x. So then you've got your derivative being negative 4 over x times x, which is going to be x squared. Fine. So in order to write the equation of a line, you need 2 things. You need the point and you need the slope. So we did all this work so we can find the slope. So the way that you're going to be able to find the slope is you need to take the x value and plug it in. So we're looking for f prime of 4. So f prime of 4 is going to be negative 4 over 4 squared, which is going to be negative 4 over 16, which is negative 1/4. So then you have slope, point, you want to write the equation of your line. So you've got y minus 5 is going to be your slope, and x minus 4. So then you want to distribute. So then here you're going to end up with a positive 1, you add over the 5, and then you've got plus 6, and that is the equation of your tangent line. So really, it's what we were doing in the last couple of problems with this one teeny extra step. Now, there is something related to tangent lines that you don't see a lot of, but it's worth knowing the terminology for it. It's something called a normal line. Normal lines run perpendicular to the tangent line. So if you were doing all of this work, but instead of having to find the equation of the tangent line, you were asked to find the equation of the normal line, you just would do all this, but here, instead of your slope being negative 1/4, you find the perpendicular slope, so then your slope would just be positive 4. You'd still have the exact same point, and you would just go through and do slightly different work. And then this would be your normal line. Okay. So, 2 more things. I want to talk about one other type of problem that crops up in your homework. And then there are a few places that derivatives don't exist. I want to talk about those places as well. And then that'll be it. Find the equation, or an equation, of the line that is tangent to the graph and parallel to the line. So you're looking for a line that needs to simultaneously do two things. It needs to be tangent to this and parallel to this. Fine. The two things that you need in order to write the equation of a line are you need a point and you need a slope. Right now you have none of those things. Fine. However, because you know that the lines are parallel lines have the same slope. So you can use this, solve it for y. And now you have a slope. We're still missing a point. Well, you know that the derivative gives you the slope at a point. So now what you want to do is you want to go through and you want to find the derivative of the function that you have. And to do that, you have to go through the limit process, which at this point you will have done about 1,000,000 times. So you've got x plus delta x cubed minus x cubed over delta x, so you'll cube that. Same thing, if you still need to write it all the way out to cube it, fine, write it out. If you can just use Pascal's triangle or cube it in your head, great. So x cubed and negative x cubed is nothing. You want to pull a delta x from all three of those terms so you can get rid of that one. Okay, so now you'll evaluate the limit and put in 0 for delta x. So that means this is 0, that'll get rid of those two terms. And your first derivative then is 3x squared. Okay, well, you know at your point, your derivative is going to be equal to your slope. So then 3x squared equals 3. Fine, so then x squared is 1. So then x is plus or minus 1. Fine. So they just want one of the equations. So you can use positive 1 or negative 1. No one cares, okay? So I'm going to pick positive 1 just because I don't feel like dealing with negative numbers. So now my point is going to be 1 comma something or other. Now this is a point on this function. So to get the y value, you just take 1 and you would plug it in. So 1 cubed, 1. So then you have point, slope, write the equation of your line. So then you've got y minus 1 is going to be 3 times x minus 1. Go through and solve for y, and that is the equation of your line that is simultaneously tangent to that, parallel to that. Okay? So, like I said, the last thing I want to talk about are places where derivatives do not exist. And there are 3. First place is at sharp turns or corners. You cannot find derivatives at pointy spots, which means like the vertex of an absolute value function, out. Functions that do that type of thing right there, you can't find a derivative. You can find it all the other spots, but you can't find it at the sharp turn. Second place that you can't find derivatives are where you have a vertical tangent line. An example of that is like square root functions. If you try to find one here, like right at your starting spot, you would have a vertical tangent line. You can't find derivatives at vertical tangent lines. The reason that you can't find the derivative at a vertical tangent line is because vertical tangent lines or vertical lines have an undefined slope. Well, if the derivative gives you the slope of the tangent line and your slope is undefined, then your derivative is undefined, which means it doesn't exist, okay? Third place is when the function is not continuous. Okay, so at asymptotes, at weird gaps in the graph, you can't find derivatives at those places because the function is not continuous. So that leads to something that you need to make sure that you keep in mind when it comes to dealing with derivatives and continuity. If you know for sure that a function is not continuous at a point, you can say that that means the derivative does not exist at that point, but the opposite doesn't hold true. Okay? Just because the derivative doesn't exist at a point, you can't necessarily say anything about continuity. Okay? Because the derivative wouldn't exist here, but this function would be continuous. Same thing here, you're continuous, but the function doesn't actually exist. Or not the function, the derivative wouldn't work out. Okay? So that is the basic introduction to derivatives. Next time we'll talk about the shortcut so that you can stop doing this all the time unless you're specifically asked to.